Okay, so we just learned about using a nulling resistor instead of trying to use a buffer to prevent our feed-forward right half plane zero from occurring. And we learned that the position of the zero, if we use this nulling resistor, is equal to 1 over the compensation capacitance times 1 over GM of the second stage minus RZ. And so the position of the zero depends on the size of RZ. So if RZ is less than 1 over GM2, then omega Z1 is right half plane 0, and we still have our phase shift issue. Whereas if RZ is greater than 1 over GM2, then omega Z1 is a left half plane 0, and our phase shift problems are ended. Now, one thing that we might try and do is to cancel out one of our poles with this newly controllable 0. So if our transfer function h of s is equal to s minus Z1 over S minus P1 times S minus P2 times S minus P3, and we want to make sure that we have the largest separation between our first and second pole. If we set Z1 equal to P2, this would mean that we'd have a larger separation between our first pole and our effectively new second pole, P3. So our strategy is going to be to do just that. We'll set the value of our 0 to be equal to the value of the second pole in our circuit, such that we get the largest separation between the two remaining poles, omega P1 and omega P3. And we're going to do so by using a MOS device in the triode region. So we're going to make our resistor that moves this, our nulling resistor, out of a MOS device. And the way we make resistors in MOS devices is to use them in the triode region. And we will look at sizing that MOS device in the next slide.